Okay, so in this mini course or module, we're going to cover resting state fMRI. I would recommend before viewing this ENIGMA-U module that you watch at least the bold fMRI, Introduction to Bold fMRI module, and perhaps even the Introduction to Functional Brain Imaging available through ENIGMA-U. So as we talked about in the last module regarding activation studies and bold fMRI studies, there's greater blood flow in areas of neural firing, which gives rise to these, you're able to plot out regional changes or local changes in blood flow that indicate greater neural firing. These are points of activation. The question then is, how are these areas connected to one another? And this is some of the questions that began in the mid-90s were being asked, not only in activation studies, but even perhaps at rest. And so network analysis really begins to ask, as opposed to identifying individual locations where there's brain activation, we now move toward not only are those locations important perhaps, but how are they interacting with one another? And so some terminology for the discussion of network analysis is, the first is node, and that's any brain region. So I pick a brain region, and if you put it in a network context, you will read and hear the term node to refer to that brain region. An edge or a link is simply a connection between different regions or nodes. The strength of the connection is the strength of the relationship between these nodes, and that's typically determined using something called a correlational analysis. And I'll show what that means in a minute, but in essence, the more strongly two areas are correlated, that value will go up and give us a stronger connection, a link. And then graph, you'll sometimes hear the term graph. That's just a network representation of the data. And so if you took all of the elements and put them together and examined all their connections, that is the graph. So what is functional connectivity? This is, I'll break this down. It's a complicated definition, but it's actually not a complicated concept. It's the temporal timing correlation between spatially remote neurophysiological events. And all that means is it's a relationship in time, temporal correlation, between spatially remote neurophysiological events, meaning spatially remote, they have to be two distinct points. They can't be the same node, although nodes, there are ways to examine a node connected to itself over time. But in this context, they have to be different nodes and how they're related to each other in their signaling. And that's the neurophysiological part. So based on that definition, if we were to apply it to a very practical example, we look at two different signals. So there's a blue and a red voxel, and they each have a bold signal time series. And so those are, remember, we need spatially remote nodes. So blue is different than red. They both have neurophysiological events. They have these time series that we can look at, the bold time series. And we can look at the correlation between them. You can see how related they are to one another. And you could ask this question if you, let's say you just picked the blue voxel, you could look at all of the voxels in the brain, thousands of them, determine which had similar time series or bold response. And in this case, it looks like these, the red and the blue voxel, are somewhat related, but those time series are reasonably different. And so it might get sort of a medium correlation. And then you move on to the next voxel, and over time, you look at those that are the most highly related to one another. And so this brings us to resting connectivity, which is dominating the network neuroscience literature, in particular in fMRI. And what that means is we can examine how the brain is connected, how parts of the brain are connected, how networks are set up without giving any task. If you remember from the last module, the example was a finger tapping task, where you tap your fingers and you stop. You tap your fingers and you stop. And then you look at blood flow that's going to some parts of the brain because they're aligned with the task, and compared to some baseline, right? In this case, there's no task. It's just the individual's lying quietly in the scanner, not sleeping, and you turn on the scanner and begin collecting data. And the A here is just the bold signal that you've seen several times in these slides. But what we know, remember, the bold signal is a secondary measure of neural firing. It has a lot of other components. It may have signal for respiration in there. It may have signal for cardiac in there. And what we want to do is take these signals out. You have to filter them out of the bold. And what you want to get is B, what we call low frequency oscillations, meaning they're slower than respiration and cardiac, which are very much higher frequency. And if we can isolate from this unfiltered bold data, if we can get these LFOs, this signal is much more closely related to neural firing. And we can plot these signals out and look at how across the brain, parts of the brain are correlated with one another. The original study by Bharat Biswal essentially did this. It did the finger tapping task that I've referred to. This is over here in A. It said, tap your fingers, stop. Tap your fingers, stop. And this is the motor cortex. And largely bilateral, in both hemispheres, motor cortex from the finger tapping task. Then Biswal and colleagues, having no task, had people just rest in the scanner and took some of the voxels in the one hemisphere and averaged that signal, and then asked the question, if I were to examine all of the other voxels in the brain, what set of voxels are the most similar? And what he found was that without having the participant tap their fingers like they did in A, that the mapping of the motor cortex emerged. In other words, this is a network that's available to us, ready to fire, oscillating similarly, even in the absence of any stimulation, which makes sense. We need to be ready to act, and therefore these regions that are wired together are ready to fire. And it's in their, it's evident in the bold signal. And so what was born from this is a range of networks, so not just the motor cortex, but other networks. So this is the example of those data. The left and right motor cortex at rest are related to one another, highly correlated. Since the time of Biswal and colleagues in 1995, a range of networks has emerged. The original work was the primary motor network, but also visual networks, what we call the salience network, frontal networks, frontal parietal, and the default mode network, which is widely studied. And it's thought to be a network associated with monitoring internal states, memories, daydreaming. And it's also thought to be the default mode network here. It's thought to be the anti-task network, although it's more complicated than that. But in essence, it drops out while we engage in goal-directed behavior, such as reading or doing a math problem. And this deactivation of DM and the default mode network has been observed in the past where, for example, there's a task, and that would be the blue here. And so the bold signal might be more evident than the posterior cingulate, which is part of the default mode network, which is in the back of the brain. You'll see that oscillates almost the opposite. You see these little diamonds. When you see these diamonds, it means that these two networks are anti-correlated, or they're one is getting out of the way for the other one. As one comes on, the other one drops out, which is very interesting that this would all be happening at rest. There's no task. It's in particular, well, in this case, pardon me, that there can be task, which makes it so the default mode network drops out but we can see the DMN in the absence of task. And here's more data showing the posterior cingulate and the medial frontal, which are the most important regions or the most widely observed regions in the default mode network. And this is their time course, shows how highly correlated they are with one another. So we now know that without any task at all, somebody can lie in the scanner, and you can turn on the scanner, and you can look at the bold signal over time, and you can correlate all the areas in the brain with one another to see which areas are most correlated with one another to create networks. So the question is, where do you look and how do you see these networks? Well, the first is a seed-based approach. What that means is you're going to look at one region and ask the question, who are all related to this one region? And the other is an atlas-based approach, and I'll show you slides for this in a moment. The atlas-based approach has the entire brain mapped out, and you get a signal for each of the identified areas in the brain based on that map. And then you can look at how those areas are related to one another. So let's give you examples of each of these. A seed-based approach is investigator determined, meaning the individual who's interested in running the study will find the seed or the part of the brain that they're most interested in and ask the question, tell me all of the areas of the brain that are related to X. And X could be, if you're really interested in memory, maybe it's the hippocampus. Or you're really interested in emotion, maybe it's the amygdala. Or you're really interested in higher cognitive processes like prefrontal cortex functions, then you pick an area in prefrontal cortex. And so these are all based on some specific hypotheses at the outset. And they have really high specificity, or they're very specific to your hypothesis, what you're interested in studying. You will define that seed. So seed-based connectivity, in essence, says, I'm going to pick my region first, and then I want to find out all of the areas that are related to or correlated with my area based on their own time series. In other words, this is one voxel that's taken from my area of interest, my seed, and now I'm going to look at the bold signal in that voxel, and I'm going to compare it all across the brain and see if others are related. And these data are fake, but you can see that these are highly related. In fact, they're identical. So this would be very highly correlated. These two areas would be connected, quote unquote, connected to each other because the signals look similar. So for an atlas-based approach, as opposed to you picking a specific seed, you could choose from a number of established brain atlases and examine how all of the nodes in the brain are connected to one another at the same time. And some of them are functionally defined, such as these are established, published brain atlases like the Power 264 and the Gordon Atlas. And they give full coverage of the brain. You may have to look for different atlases depending on your exact interest, but most of them give full coverage of the brain. And then what you would do is look at the connectivity across all of the regions and create these connectivity maps. And again, the way these are links or edges, connections between the nodes or the regions in the brain, those edges or those connections are weighted. So some of them are lighter and some of them are darker. So the darker would be a stronger connection. And that connection is really just based on, are those two signals, the bold signal time series, are they similar? Or if they're different, for example, this node here, some of the nodes you can look at and see there's no connection between them, which means that the signals are quite different. So those two nodes aren't directly connected. So in summary, for network neuroscience or resting state fMRI, the brain is never truly at rest. Even when you're sleeping, the brain is highly active. But we can observe how it functions without a task or any stimulation at all. Resting state fMRI uncovers existing networks that are always ready to be used. And the example was from Biswell et al.'s really important paper examining motor networks. Examiners must eliminate other signals from the bold signal, including heart and breathing, in order to isolate parts of the signal that are related to neural firing. So remember, the bold signal is only a proxy or a secondary measure of neural firing. We want to get it as close to that link as possible. And there are other parts to the bold signal, the raw data, that we have to filter out in order to do so. And then finally, resting state methods allow us to look at macro scale or large scale brain organization. So we're not talking about connectivity at the synapse, and we're not even talking about directed connectivity based on white matter pathways. We're talking about two related signals that, if they're high enough, the correlation or the relationship between them is high enough, we refer to them as connected. And we can map that out across the brain with hundreds, and there are atlases with even thousands of nodes or brain regions that you can determine the relationship between. And that is it for resting state fMRI.